In this video, we're going to talk about the complex derivative and the Cauchy Riemann equations. So let's go back to Calculus 1 for a moment. The definition of the derivative says that f prime of x is the limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. You may have seen this definition where h is used instead of a delta x, but the idea is the same. Now in this limit, we assume that delta x is a real number. It can be positive and approach 0 from the right, in which case we use the notation delta x goes to 0 plus, we use a superscript there. Or it can be negative and approach 0 from the left, which we can express as delta x goes to 0, and then we put a superscript minus. And if f prime of x exists, then these two limits must be the same. So a picture might look something like this. If we're interested in the derivative at x, we can move delta x units over, in which case delta x is positive. As delta x goes to 0 from the right, this point is going to move that way. Or we could write x plus delta x, where delta x is negative, we could draw that point over here. And as delta x goes to 0, x plus delta x is going to approach x. So if we let delta x go to 0 from the right, or we let delta x go to 0 from the left, the two limits have to be the same. In terms of this graph, if x plus delta x goes to x from the right, or if it goes from the left, the limit should be the same in the derivative definition. Now the complex derivative is defined using the same limit notation. F prime of z is the limit as delta z goes to 0 of f of z plus delta z minus f of z all over delta z. Now the important thing in this definition is that delta z is a complex number. So let's take a look at a simple example. F of z equals z squared, and let's use this definition. So we proceed very much like we did in Calculus 1. So f of z plus delta z minus f of z over delta z. This is the definition of the derivative. So our function says take z plus delta z and square it. So we would put that here, minus z squared divided by delta z. We expand this expression. We get z squared plus 2z delta z, 2z delta z plus delta z squared minus z squared over delta z. And the z squareds cancel. And then we can factor out a delta z and cancel that because we know that delta z is not 0, so I can factor a delta z out of the numerator and cancel it with this one down here. As delta z goes to 0, this thing is basically going to 0, so we're simply left with 2z. And that kind of makes sense because in Calculus 1 we know the derivative of x squared is 2x, so now we know the derivative of z squared is 2z. Many of the usual derivative formulas hold in the complex setting. The power rule, for example, if f of z is z to the n and f prime of z is n z to the n minus 1, similar derivative rules hold for the exponential, the sine, and the cosine. For the log, the principal branch of the log, where I'm using a capital L here, then f prime of z is 1 over z, provided z is not in the form of z equals x, where x is a real number less than or equal to 0. In other words, z is not on the negative real axis, nor is it on the origin, which we call the branch cut. Now, if f has a derivative at each point of a region D in the complex plane, then we say that f is analytic or holomorphic on D. Those mean the same thing, the words analytic or holomorphic. If f happens to be analytic in the entire complex plane, we say that f is an entire function. For example, the functions f of z equals e to the z, sine z, cosine z are all entire functions. The function 1 over z is analytic in the complex plane, the domain consisting of the complex plane with the origin removed. We sometimes refer to this as the punctured plane. The function log of z is analytic in the set of numbers whose arguments are non-zero and whose moduli is greater than 0. Z is not on the real axis, nor is it at the origin. So again, that's the branch cut. Now, an important part of this definition is that delta Z goes to 0. It's any complex number that approaches 0. Now, in Calculus 1, where x plus delta x goes from either the left or the right, that's all we have to consider. But in the complex setting, z plus delta z can approach from infinitely many directions. Now, we're going to take a look at that implication in just a moment. But let's just look at a property of complex functions in general. Every complex function can be expressed in terms of its real and imaginary parts. For example, suppose f of z is z squared, then if z is equal to x plus iy, f of z is x plus iy squared. And if we expand that, we would actually get x squared minus y squared plus 2xy times I. We call the real part of this function the stuff that is not multiplied by I, that's x squared minus y squared, and the imaginary part is the part that's multiplied by I. It's 2xy, not 2xyi. Now these are each functions of two variables, the types of which we discuss in multivariable calculus, so they each have to have partial derivatives. So let's take a look at those partials. Let's take a look at our definition and let z plus delta z approach z two different ways, along a horizontal line through z as well as along a vertical line through z. So the picture would look something like this. Here's the complex plane. Here's a fixed point z. We're going to let z plus delta z approach 0 this way, and approach 0 that way, and approach this way. So let me say that again. We're going to focus on the point z, and we're going to choose a point that approaches z, let's say from the left, approaches z from the right, approaches z from above, and approaches z from below. Now, if we go from the right, we can write z plus delta z as z plus delta x, because we've simply moved in the x direction where delta x is greater than 0. This point over here can be written as z plus delta x, where delta x is less than 0. Now, if we go up to this point here, we've gone up an imaginary amount. So this would be z plus I times delta y, where delta y is greater than 0. Similarly, this point down here, because it's directly below, would be z plus I delta y, where delta y is less than 0. This length is delta x. This length is delta x, this length is delta y, and that length is delta y. And the idea is that if we let delta z approaches 0 from any one of these four directions, in fact many other directions as well, including many, we need to get the same limit in order for f prime of z to exist. So we'll let z plus delta z approach z in two different ways, along a horizontal line through z as well as along a vertical line through z. Okay, so let's suppose first that delta z is delta x. That corresponds to z plus delta z going to z along a horizontal line through z. Now in this case, z plus delta z is x plus delta x plus iy. In terms of my picture, we're looking at this situation, z plus delta z is the same as z plus delta x. Or over here. So, z plus delta z is x plus delta x plus iy, because z is equal to xy. So if we substitute z plus delta z into u and v, our real and imaginary parts, this is x plus delta x, this is y, this is x plus delta x, and this is y. So again, z plus delta z is x plus delta x plus iy. So we're taking this, substituting it into the first component of u, the first component of v, and we're substituting y into the second component of each. So f prime of z is the limit as delta z goes to 0 of this. That's the definition of the derivative. But we've already said that we can express f of z plus delta z this way, so we're going to substitute that in. And we know that f of z can be written this way in terms of its real and imaginary parts. And in this situation, delta z is the same as delta x because delta z is approaching 0 from the right or the left. So we're going to collect terms here, u of x plus delta x y minus u of x y. So we're combining this term and this term. And then we're going to combine this term and that term and factor out an I. And that's what we get. Then we're going to break this limit up into 2. So we'll take all of this stuff, put it over here. We'll take all of this stuff, put it over here, and we can factor an I out of that second limit. Now, as delta x goes to 0, this is a partial derivative where we're treating y as fixed. So it is the partial derivative of u with respect to x at xy. This whole thing collapses to be the partial of u with respect to x at xy. This whole thing right here, this limit, works out to be the limit, the partial of v with respect to xy, but then we have this I out in front. So we're going to hold on to this for a moment. Now suppose we let delta z equal I delta I, which corresponds to letting z plus delta z approach z along a vertical line through z. So in this case, we're going to be focusing on letting delta z go to 0 from above or below. So we're going to be looking at that direction of approach in that direction. So z will be I plus delta y, and x will be fixed. So in this case, z plus delta z is x plus I times the quantity y plus delta y. Now, f of z plus delta z will be u of x, y plus delta y, plus I times v of x, y, delta y plus delta y. Let's substitute this into our definition of the derivative. This is the definition of the derivative. Z is equal to, as we said before, this will be u of x, y, delta y. This will be I times v of x, y plus delta y. So this whole expression right here corresponds to that. And f of z is simply all this stuff over here. Now we're dividing it by delta z, but in this case, delta z is equal to y plus delta y right there. Let me phrase that, yeah. Delta z is equal to simply I times delta y. So delta z, this becomes I delta y. And again, we're going to group like terms. We're going to combine this term and that term right there. We're going to factor an I out and combine this term and that term right there. And all of this is over I delta y. And again, we're going to break the limits up into 2. So we're going to take this stuff, which we have right there. So this term divided by that. We're going to take look at that expression, and then we're going to look at this stuff as well. Now you notice that when we break this up, we're going to have an I in the numerator and the denominator, which cancels. So we have no I stuff over here. Whereas when we take this and divide it by I delta y, that I appears. Now we let delta y go to 0. This is a partial derivative. As delta y goes to 0, this becomes the partial of v with respect to y. This stuff, except for the I, becomes the partial of u with respect to y. But then we have to divide by I right here. So all of this reduces to be this quantity. Now dividing by I is the same as multiplying by negative I. So we can get rid of the I, we can move it into the numerator by putting a minus sign there. Now on the previous page, we use the definition of the derivative to show that f prime of z had to be the partial of u with respect to x plus I times the partial of v with respect to x. That is when we let delta z approach, we let z plus delta z approach z from the left or the right. On the other hand, we've also been able to show that f prime of z equals this expression, which involves partials with respect to y. So if we take this expression, put it over here, and use the expression from the previous page, we have that. Now, the real and imaginary parts of both sides have to be the same. That means that this quantity has to match up with that quantity, and this quantity has to match up with that quantity without the I. So we get two equations. The partial of u with respect to x equals the partial of v with respect to y, and the partial of u with respect to y minus that quantity is the partial of u with respect to y is minus the partial of v with respect to x. And these equations are known as the Cauchy Riemann equations. And they have to hold in order for f prime of z to exist at a particular point. So in other words, if f prime of z exists at a point, then the Cauchy Riemann equations must hold at that point. Now the opposite, or what mathematicians call the converse of that statement, in general is false. Let's take a look at an example. We discussed f of z equals z squared a moment ago. Its real and imaginary parts are x squared minus x and 2xy, respectively. Let's take the partial of u with respect to x. We treat y as a constant, so we get 2x. Let's take the partial of v with respect to y. We treat x as a constant, and we get 2x. These quantities are equal. Let's take the partial of u with respect to y. We treat x as a constant. We get minus 2y. Let's take the partial of v with respect to x. Well, if we take the partial of v with respect to x, we get 2y. But if we tack on a negative sign, we get minus 2y. So the partial of u with respect to x equals the partial of v with respect to y. That's the first Cauchy Riemann equation. And the partial of u with respect to y equals minus the partial of v with respect to x. So the second Cauchy Riemann equation holds. Let's take a look at another example, the inversion function. Suppose we define f to map from the punctured plane, the complex numbers minus the origin, into the complex numbers 1 over z. Let's denote z equals x plus iy, and let's take this function and break it down into its real and imaginary parts. So f of z is 1 over x plus iy. To get the I out of the denominator, we multiply the numerator and the denominator by the complex conjugate, which is x minus iy over x minus iy. The numerator is x minus iy. If we expand the denominator, we get x squared plus y squared. Breaking this up into its real and imaginary parts, we get x over x squared plus y squared, and we get minus I times the quantity, I times the quantity minus y over x squared plus y squared. So my u of x is this, and my v of x is all of that. And the partial of u with respect to x has to equal the partial of v with respect to y. And the partial of u with respect to y has to be minus the partial of v with respect to x. Let's take a look at the partial of u with respect to x and use the quotient rule. The quotient rule gives me a numerator that looks like this and a denominator that looks like that. Remember that when we apply the quotient rule to this, we are treating y as a constant. The numerator here simplifies to y squared minus x squared, and the denominator is x squared plus y squared squared. So this is the partial of u with respect to x. If we take the partial of v with respect to y, we want it to equal the same thing. Let's do that. Again, we're going to use the quotient rule. The partial of v with respect to y can be written as such. I'm using the quotient rule. If we simplify the numerator, we get y squared minus x squared over x squared plus y squared squared. So that says the partial of u with respect to x, which we got on the previous page, equals the partial of v with respect to y. So the first Cauchy Riemann equation holds. And the calculations for the other equation are very similar. And of course, throughout this discussion, we're assuming that z is not the origin. Let's take a look at a different example. Suppose f of z is defined to be the norm of z squared. Now in this case, let's write z equals x plus iy. F of x would be this should be z. F of z would be x plus iy quantity squared. The length of that squared. And I'll let you expand this and you get x squared plus y squared. Now notice that there's nothing involving I here. So that means u is all of this. And v is just 0 because there's no imaginary part. So the partial of u with respect to x is 2x. And the partial of v with respect to y is 0. And these two aren't equal unless x is equal to 0. If you use similar reasoning, the partial of u with respect to y is 2y. And the partial of v with respect to x minus the partial of v with respect to x is equal to 0. And these are only 0 at y equals 0. Therefore, the Cauchy Riemann equations are satisfied only at z equals 0, which implies that this function is not analytic in the plane except possibly at the origin. Here is your exercise in preparation for class. For each function below, determine the real and imaginary parts, u and v, having the property that f of z can be written as thus, where z is x plus iy. Then determine whether the Cauchy Riemann equations hold. The first function is the exponential function, e to the z. So what I would suggest doing first is writing this as e to the x times e to the iy, and use the Euler's formula to expand this in terms of cosines and sines. Now let f of z equal z bar, where z denotes the complex conjugate of z. For each of these, find the imaginary and real parts and determine whether the Cauchy Riemann equations hold.